Okay, so what did we learn yesterday? Now to the boring stuff, right? What's that? So, okay, before flow, what did we learn about? Okay, particle density. Then, how do we measure particle density? Or what are the three different types of particle density we measure? What's envelope density, right? So then, uh, what did we talk about after particle density? Go ahead. Okay, measurement techniques. Okay, so how do we measure particle density? Pycnometer, okay, liquid pycnometry, gas pycnometry, right? Then after particle density, what did we talk about? Powder density, right? So in powder bulk density, the what are the things that we learned yesterday? Hopefully you remember. Man, what did we learn in powder density? Someone murmuring. You don't remember? Hassner ratio, okay, what else? So how do we calculate Hassner ratio? Okay, routine. Okay, tap density over bulk density, right? Area-rated bulk density, right? So, and then we talked about Kawakita and Ludde constants, right? It's related to bulk density and compressibility, right? So, what are the different types of powder density that we talked about yesterday? Okay. Okay. In bulk density, what are the different types of bulk density that we talked about? What's that? Okay. Tapped, compacted, right? So again, their applications are different, right? So, and again, depending on your end purpose, you will have to choose the appropriate density measurements, right? Is that right? Anything else? So how do we measure compacted bulk density? Anyone remember the name of the instrument? I did not explain much, but it was on one of the slides. Okay. Can you see in your actual testing machine, right? But there is specific instrument called odometer. Okay. So that measures compacted density. Okay. So in powder flow, what did we learn about yesterday? Okay. So what are some of the traditional flow assessment methods, like qualitative indicators? Okay, angle of repose. What is that? Okay, angle of fall, angle of spatula. What else? Still, there are more. Okay, I'll come back to that. Uniform, yeah. What is that? Yeah, okay, difference in dynamic angle, exactly, yeah, dynamic angle of repose. What else? Compressibility. Okay, so compressibility, that's where we use some ratios, right? So what are the couple of cars ratios that we talked about, or cars flow indicators that we talked about? Yeah, two types. What? Flowability and floodability, right? So flowability, we use 4 different parameters, and then floodability, he used 4 different parameters to get those get those indices, right? So based on the indices, you calculate, qualitatively check the type of flow behavior, right? So what else did we learn? So one more thing, last thing before we ended. Rheometers, yes. So powder rheometer, right? Especially, we talked about FT4 or Freeman Technologies powder rheometer, right? So talked about basic flow energy, specific energy, aeration, permeability, etc., right? So again, those are, whatever methods that we talked about yesterday, most of them are traditional, qualitative indicators. right? So it helps with ranking of powders, right? We talked about one example, right? Sugar and coffee powder, right? So if you wanted to rank sugar and the flowability of sugar and coffee powder, all these methods can help. One might flow better than the other, right? But the actual flow testing, or math-based flow testing or physics-based flow testing, we do that by shear cell analysis. Okay, anyone have used shear cell or seen a shear cell shearing device? No. Okay. Oh. Okay, so we measure the powder's yield strength. Okay, so yield strength means the strength of the powder, how much strength it takes to move one layer of powder over the other layer of powder. Okay, so that's the yield strength, yielding. Okay, moving. Okay, so that's the yield strength. It's a function of the stress. How much load is acting on the powder. Okay, so we measure the strength and stress. Again, calculate their flow behavior using these two relationships, strength and the stress. Okay, and again these are math based, so we can use these values whatever we are getting from this test to design hoppers, bins, to rate the flow behavior, comparative purposes. Most commonly, if you are designing a hopper or bin or even a handling device, you should know some, their flow properties. And flow properties means, how you measure using a shear cell. Okay. So shear cell will, go through some of the properties that we will measure, using a shear cell. Okay. So one of the, some of you might have seen this, word, right? Unconfined yield strength. Okay. This is one of the basic parameters that we test using a shear cell. Okay. Not this way, but unconfined yield strength. Again, how much strength it takes to make the powder flow. Okay. So in traditional measurement, you can measure this using a uniaxial testing machine too. Okay. So you compact the powder, okay, and then apply additional stress so that it breaks and it flows. Okay. The breaking indicates flow of the powder. Okay. So that's called the unconfined yield strength. Okay. Unconfined means again the powders are not confined on the site, so they are free to flow. Okay. And then yielding, or the point or the pressure at which it yields or flows, is called the unconfined yield strength. Okay. It's clear?
So what is it? So you said side layer, the first layer, and the later layer.
This
That is
one.
showing the boundary only, no?
Mm-hmm.
So how does it become unconfined then?
So this is the compaction process. You compact confining in under confined wall, then you remove these walls. Okay, you see those walls are not here. Okay, then apply more stress or force, and at one force, it breaks.
When we define the period plane, there we are removing the plate.
Yeah. So that's again unconfined, right? So you'll have to keep it free. So the boundaries are free. Okay, free to move. Okay.
Sir, here we measure our do unconfined one.
Yeah.
Separate the two layers.
Yeah. So that's what
How
for.
much? How much force are required?
Yes. So 2 layers means, as I said, for a powder to yield or move over one layer over the other layer. That's the flow, right?
Yield means
Yield means flowing, like moving.
okay.
Okay. So if you for example, if you take about, I'll talk about that in a minute too. If you have a hopper, right? So if you have powder, you're opening the hopper outlet, okay? So then it's unconfined, right? So then the powder has to flow, right? So that's almost, not almost, exactly that's what here, it's correlating here. You're opening the bin walls, bin opening, and allowing the powder to flow, okay? And at what strength the powder flows is what we are measuring. Okay, clear? But again, oh yeah, this is the one. So what do we care about unconfined yield strength? So when we open the bin hopper, okay, so usually the powder has to break free from this bottom layer, right? So the powder has to flow from here, right, from the bottom. So But due to this Hopper dimension, Hopper characteristics, there will be some strength in the powder here, right? So this strength of the powder here should be higher than the strength at this arch. So then only it will push the powder down. So that will make the powder flow. Okay? But if the strength at this arch is higher, that's when the flow stops and there will be caking, holding of powder, etc. Non-uniform flow, etc. Okay? Is that clear? Any questions?
So it depends on bulk density or cohesiveness.
Lots of factors, particle properties and also the Hopper dimensions. Hopper dimension, Hopper angle, Hopper, wall friction, etc. We will go through some of them. Okay?
So which we have lastly we are discussing about funnel hopper, mass flow.
Yeah.
Which hopper?
Yeah, any hoppers. For any hopper, the strength of this powder should be higher than the strength at this layer, okay, for the powder to flow. It could be a mass flow hopper or funnel flow hopper. If the strength here, if it's not well constructed or well designed, then the strength at this arch will be higher.
So it doesn't depend on stagnant. Some funnel flow means stagnant is there.
Yeah.
Effect wavelength.
So I'm not talking about anything flow, anything from here. I'm just talking about this breaking of this layer and flowing. Okay.
So it's depend on flow also and structure also.
Yeah. So flow, structure, yeah, that's what lots of properties influence this.
Yes.
So not only one property. So funnel flow, mass flow, you change the Hopper angle, right? So that's one major parameter. But we are, what we are doing in this shear cell testing is using all these properties, okay, powder properties, how it yields and how it, flows to design the Hopper angle. Okay, so one basic thing that we are designing is designing the Hopper angle. So based on their properties, you can design this appropriate angle so that the strength at this layer is low. Okay, is that clear? But I'll show you some examples, okay, about Hopper design, etc., okay, or Hopper angle calculation. So one of the, again, common, property that we calculate, again, from that, consolidation or unconfined yield strength is called the material flow function. So material flow function is the relation between the normal stress and the unconfined yield strength. Okay? So normal stress is this, stress at which you are consolidating, okay, sigma 1, okay, and that's the consolidating stress, and then unconfined yield strength is the stress at which it's breaking or flowing. Okay? So at different consolidation stress, your unconfined yield strength will also be different. Okay? For example, if you are increasing the consolidation stress, then the unconfined yield strength will also be high. Okay? It's clear? Any questions so far? So again, lots of other factors, other than powder property, Hopper properties, environmental conditions play a lot of role. Okay, humidity, moisture content, temperature, etc. Because humidity and temperature makes the powder cohesive, right? So that will affect, and again, other properties. We talked about vibration, right? So vibration affects those, testing or parameters. There are, I will not talk about this, but there are shear cells that can measure the effect of vibration too. Vibration and consolidation stress and the unconfined yield strength too. Right? So again, time consolidation is another factor, right? So most commonly we use bins for storing the powders, right, or any granular material. So over a period of time, from its own weight, it adds strength to the powder, right? So that's called time consolidation. So due to increase in time at storage, and also increase in time at storage, many powders cake. You all know about caking, right? We briefly talked about it, right? So caking of powder is a big issue. When you increase the storage time, the powder can cake, okay? And not the eating cake, okay? It's, you all know, right? At least for agriculture student, it's caking is like agglomeration of powders, okay? So it gains strength Mainly, losing permeability, losing interstitial, air spaces, the powders become more cohesive. There could be some moisture absorption and adsorption that leads to bridging between particles, and then they can cake too. Okay, and other fragmentation, plastic deformation, chemical reactions, etc. Chemical reactions, common if you are storing crystalline solids. Okay, amorphous solids. Unless and otherwise, if the humidity is very high and temperature is very high, you might not see many chemical reactions, but crystalline solids can, change over a period of time due to chemical, changes. Okay. Any of you have learned about liquid bridging, solid bridging, etc. between powders, particles. It's very common in food powders. If you're working on food, again, just Google and see deliquescence. Okay. Then again, deliquescence is surface melting of food powders. Okay. It's common in food and pharmaceutical powders too. When the powders absorb water, the surface starts melting, and when it starts melting, then it forms bridges between particles. It forms liquid bridges, then it turns into a solid bridge, then caking occurs. Okay. So time consolidation effect also, again we can check by calculating or determining the material flow function. Again, material flow function is the relationship between consolidating stress and the unconfined yield strength, right? So in general, what we do is, for shear cell testing, okay, what we do is, you take 3-4 batches of powders and put some dead weight over it. Okay, put some 5 kilogram weight in one batch of sample, put some 10 kilogram weight in one batch of sample. That adds to the load, right? And keep it for some 2 days, 5 days, a week, 2 weeks, then test their unconfined yield strength. Okay, that's what we commonly do. So increase in time consolidation in general, the unconfined yield strength will also go up. Okay, so amount of strength needed to make the powder flow will also go up. Okay, due to the effect of time consolidation. Okay, clear? No? Are you here? You're here? Okay. Any questions? Okay, so again, the flow factor that's calculated from the their material flow function. Again, that's the inverse of the slope of material flow function. So MF is material flow function. So flow factor gives the inverse of the slope. Okay, so it's a ratio between stress over unconfined yield strength. Okay, so we calculate slope by, how do you calculate slope? Y over x, right? So here it's inverse of slope, that's x over y. Okay, so again, based on that flow factor, you can define the powders. So usually if it's around 1, it's very hardened powder, but if the flow factor is high, then it's free flowing. Okay, that means the powder can flow freely in any type of bin. Okay, so you can get that, right? So if the consolidating stress is higher than the unconfined yield strength, okay, so unconfined yield strength, we talked about it, right? It's on the bottom arch, right? So if the consolidating stress, that means the stress within the powder, within the bin, if it's very high, then this strength at the arch, okay, then their flow will be better, free flowing. Okay, so that's again the ratio of sigma 1 over unconfined yield strength. Okay. So again, but if you take any powder, it might not fit in one category. Okay, so it might change their the powder's behavior change based on the consolidating stress and the unconfined yield strength. For example, the same powder, you are dealing with powdered sugar. Okay, so it might be it might not flow very well at smaller consolidation stresses. Okay, I'm just giving an example, but that might not be right. But if you increase the consolidating stress, then it might go into a free flowing category. Okay, so that's why it's very important to test at different consolidation stresses and at different conditions. so that you can accurately get their flow behavior. Okay? Any questions? Yeah.
Sir, how these factors arises, like 10, 4 to 1?
So this is again by checking the different, that's a very good question. So by checking different powders, okay. So it's arbitrarily designed, if it's less than 1, it will be very hard and it doesn't flow. You can derive this mathematically too. So if the consolidation stress is same as unconfined yield strength, then the arch at the bottom will not break, right, because it has high strength. So that's again almost that criteria. If the consolidating stress is very high than the unconfined yield strength, then it will flow very freely, right? So the powder will break very easily from that bottom. Okay. Any question? Okay. So just a quick question. So which powder will have a better flow properties, A or B? B. Okay, great. Any other thoughts? So for this question there is more than 2 options. Okay. So if I said B is wrong,
A, sir.
okay, A is also wrong. Okay. Any other thoughts? Okay.
Beyond that meeting and Fred Hayes' meeting, beyond that, that will be I think same.
Okay.
And above that, B will be free.
Okay. So that's what very important to characterize the powders, right? So it depends on the consolidation stress. So at lower consolidation stress, you can see A will have a better flow properties. You might remember, right? So it's poor flow to free flowing, right? But at a higher consolidation stress, okay, B is having a better flow property than powder A. Okay. So powder properties and the stress or the type of bin will affect the individual. You have a question? Go ahead. What was the question?
Sir, if we consider like for time, then A is good in flowing behavior.
No, we are not talking about time consolidation here at all. It's one time, fresh powder, for example. Fresh powder, you are consolidating at different stresses. For example, 5 kilopascal, 10 kilopascal, 15 kilopascal, etc. Okay. So it's not the exact value, I'm just throwing out the number. For example, at 5 kilopascal, consolidation stress, so you can assume a small bin, like 10 kilogram bin, okay. Then the powder A will have a better flow property, okay. But if you're, storing the same powder in a ton capacity, bulk bin, okay, then, B might have a better flow property than A, okay, just for comparison. So again, so that's again shows the importance of characterizing, okay. So if you have powder, you'll have to characterize them well to replicate different conditions, okay. Okay, so then this another example here, comparing some of this again pharmaceutical powders. So this is lactose, again you can see their flow property changing from poor to better, like little bit conditions changing at higher consolidation stress, okay. But for some powders like sulfate, lactose, etc., they in general have better flow properties, okay, irrespective of consolidation stress. Okay, any questions before we go on to the next actual testing? So we can replicate all those in instrument, okay, that's called the shear cell, okay. So shear cell, this is what it replicates, as we talked about, you test the powder at different consolidation stress and then get the unconfined yield strength, okay. So it's usually performed as a quasi-static test, that means you have the powder bed fixed, and then when it starts moving, slowly changing from static to dynamic, that's the point that's called, the incipient yield. That's the point at which we measure their stress and strength relationships, okay. And again, as we talked about environmental conditions, sample preparation is also very important. Okay, so when you pour powder, in a sample cell, you don't want to unknowingly consolidate them, right? Then you are adding more strength, like artificial strength to the powder, right? Extra strength. So most of the instruments, you'll have to pour the powder through sieve, shear cell testing, so that it's uniformly filling within the shear cell, the cup or the holder. Okay. And again, the shear cell testing, it helps with calculating the angle of internal friction. Okay. That again, that's a derived property. This is not coefficient of friction, but this is a derived property, and also helps us calculating the wall behavior. Okay. How does a powder interacts with different wall materials? Like if you're storing powder in an aluminum bin compared to a stainless steel bin, okay, how does it affect their flow properties? Because their friction properties, their strength will be different, right? You can take aluminum, you can take stainless steel or any other type of steel, their property changes, right? So again, different, it helps with wall effects. So they don't, using shear cells, we don't get the measures directly, okay, but we use Mohr circle analysis. Okay. Most of you would have learned about Mohr circle analysis, right? At least ag engineering students. Anyone remember Mohr circle? No? Agriculture engineers? Suna? Okay. What's that? Yeah, hardness, when you learn, hopefully in second year of your ag engineering, you would have learned in strength of materials class, right? And it's a difficult class, but you all passed in strength of materials? Yes, okay. And if not, you will not be here, right? If you didn't pass, okay. But I know it's a difficult class, so you would have learned about Mohr circle. So again, for other students, Mohr circle analysis is the analysis of stress and strength on, structural, structure when it goes through some stress and strain. Okay. Well, I'll give a brief, note, but we will not go into those calculations here. Okay. So it's a typical, shear cell, Jennike shear cell, and again, I briefly talked about it yesterday. So Jennike is one famous researcher who solved most of this, or who derived all these, fundamental math behind this powder flow. Okay. And he developed a machine too. So Jennike shear cell, and how does it work is, this is a sample cell, so you fill the powder, okay, and then you apply some normal force, that's a consolidation sigma 1, okay, and then you apply some shear force, that's the force that needed to move one layer of powder over the other layer of powder. So you slowly apply the shear force, and at one force level, the powder starts moving, okay, the instrument starts moving. So that's the point at which we calculate all the other characteristics. Okay. So what are the, again, I'll show some more examples. So this is a different type of annular shear cell, a ring shear tester. It's also very common. Schulze, again, it came from Germany. Very similar testing, but you can see kind of small grooves that helps with easy measurement of powders. One of the challenge will be, again, using larger size particles will be little difficult in this ring shear testers. For powders it works very well, but if you are using like granulated sugar, then you might not get a uniform value. Okay. So how do we draw again Mohr circles? So from the this testing, you get two values, right? Normal force and then the shear force, right? So we use those two, okay. So the applied normal stress and the shear stress, right? But you are applying force, but you will have to calculate stress, right? So how do we calculate stress from force? So force over unit area, right? So from those unit area, you calculate the stresses. So you relate those points, okay. So at different applied normal stresses, you get different shear stress values. And then that line that connects all those points is called yield locus. Okay. So above this point, the powder will flow freely. Okay. at these conditions. Again, we will go through some of those applications in a minute. Okay. So, when you get that point, again you are not getting any meaningful information from those points. Okay. So, then using those points and from the yield locus we draw 2 more circles. You can draw more than 2, okay, but primarily we draw 2 more circles. So, I am showing only half of this here, it will be a circle. Okay. So, but when we talk about powder flow, at least it is in 180 degrees, right, it is a plane. So, we take half of the circle. Okay. And I am not again going into the calculations, but if you are, for example, studying about twisting of metals and cylinders, then you will have to draw a full circle, okay, more circle. But for powder it's plain, so we half circles, one minor Mohr circle and the other one will be the major Mohr circle. Okay. So, the minor Mohr circle, so again these are drawn, again most of these instruments now have automated softwares that gets those circles for you. Okay. So, the minor Mohr circle you start from the origin and then just touch the line, the yield locus line, and then draw the circle. Okay. So, that using that origin and just touching the line you draw a minor Mohr circle. Okay. So, the major Mohr circle will be touching at the end point of the the relationship between applied and shear stress. Okay. So, touching the last shearing point you draw another circle, that is the major Mohr circle. Okay. So, you draw 2 circles and then you get the other values such as unconfined yield strength. So, this will be the unconfined yield strength. So, the right hand side of the minor Mohr circle. Okay. You get the major principal stress that is acting on the powder at that shearing point or for that yield locus. Okay. And also you get the minor principal stresses. Okay. Hopefully I have one more picture that will explain this major and minor principal stresses in a minute. Okay. So, a couple of other points that you get is again cohesion. Okay. So, the intercept, the value here, the value from origin to this intercept is called cohesion. Okay. Any of you remember Mohr-Coulomb law? Okay. So, that is C is the cohesion, right. So, tau is equal to C plus sigma
Sigma is like
normal stress, right. So, that is the cohesion. Again I will show the equation for others, okay, in a minute. Okay. So, that is the intercept here. Okay. So, that is the cohesion of the powders. Okay. And we get effective angle of friction or effective angle of internal friction when you draw a tangent to the major Mohr circle. So, you draw a tangent to the major Mohr circle and that angle gives the effective angle of internal friction. Okay. So, that is the friction at which above which the powder will flow. Okay. So, again this is not coefficient of friction, but this is angle of internal friction. This is a derived property from material testing. Okay. Any questions? I thought I have the a figure, but it might be. So, if you take an unconfined yield strength, okay. So, we know the side is confined, right, when you are applying stress. So, this will be sigma 1, right, that is the applied strength stress that we are applying to compact the powder. So, the stress acting on the side walls is sigma 2 here in this Mohr circle. Okay. So, that will be the minor principal stress, again that is helping to compact the powder, though you are not applying any force or stress on the sides, but still due to the confinement there will be stress, some stress acting on the powder. So, again this is sigma 1, again that is the end point of major Mohr circle, and then the starting point is sigma 2. Okay.
sigma 2 is acting due to the compaction of the powder, right?
No, from the side walls, from the side wall. Okay. So, the pressure from the side wall during compaction, yes, it is confined, right, it is not moving. So, there will be some stress that acts on the powder to compact. Any questions?
After compaction, we will go for unconfined test,
Yeah.
removing the word.
Yeah.
So how do you know that the powder is compacted and now we can go for the unconfined test?
So it depends on the powder. You will have to make sure it's compacted. So you should, by trial and error. Okay. So you might, if it's difficult to compact, then you'll have to increase the pressure.
It may fail if when we remove the word.
At smaller loads it fail, but at higher loads it usually forms a compact. Okay.
By trialing
Yeah.
jams.
Yeah. So in general, we'll talk about that, selection of stress too. In general, it's related to your bin size. So if you are storing in like 10-ton, bin, then you will have to pick some distances within the bin and choose the stress at those heights, and then use that for compaction. But that's those stresses that we will be using here, applied normal stresses too, right? Is that clear? But again, we will talk about that in a minute. Okay. So again, solid fraction. We talked about solid fraction yesterday, right? Yeah. So solid fraction amount of powders, right? So depending on the solid fraction, this behavior might change initially, at least at the initial points of compaction. Okay. So again, solid fraction is the amount of solids present within that sample, right? Within that amount of sample you take. Okay. So sometimes if it's a loosely packed powder, not sometimes, most times, if you're just putting the sample in the shear cell and then start shear testing, the powder might compact, okay, and again that might lead to wrong results. But again, for initial stresses, I'll talk about that in a minute. Okay, but if it's a tightly packed powder, okay, it might dilate, it might loosen up, okay, and then again, I'll not go into dilatancy. So it depends on the type of the powder. Okay, so the powder or the stress state at which it's not changing any volume, or if the solid fraction is not changing, it's called the critical state. So that's the state at which you measure the shear stresses. Okay, normal and shear stress. For example, if the powder is consolidated, it takes some time to get to the the powders to reach that critical state, so that you are actually measuring the flow behavior rather than their consolidation or over consolidation. Okay. So again, when you apply those, again under consolidated might behave differently, over consolidated, but sometimes you will see those change in strain when you start applying those shear forces. Okay. Okay, for 5 bonus points for tomorrow's exam. Okay, can you give me one example of powder, okay, or solid material that when it's tightly packed, it dilates, loosens up. Okay, so dilation here means dilation is the powder will change in volume, but it will not change in shape. For example, if it's in cylindrical form, okay, still the volume might change due to the moving of the particles inside, but the shape remains the same. Okay. Any example, but I'm sure all would have seen that example. Okay, at least 99% of you. Any quick thoughts? Generally, it should be cohesionless, right? If it's cohesive, it might change in shape, right? So that's one clue. So it's not like food powder, okay? That's another clue. It's not a food powder, okay? Food powder also there could go through some dilation, dilatancy, okay? What is that? Do you have answer? Or huh? Exactly, sand. That's very good. It's most commonly it's beach sand, okay? So if you compact beach sand, then again, so I should give you 5 bonus points tomorrow, right? Okay. So when when you check, you can check, when you go to any beach, if you compact them, using your hands, it might, you will feel that moving of particles inside, but still the volume, you are holding it, right? So the volume doesn't change, okay? So many powders will go through those dilation, and I'm not included here, but the stress that leads to that dilation is called deviatoric stress. Okay, that leads to that change in that dilation. Okay. But most common you will see in food powders is this, when you put the powder in shear cell, it might consolidate a little bit, it might over consolidate before it reaches the critical state. Okay. So how does we test this? Testing procedure, it's very similar to like this compaction process, but here compaction process we will have to change the powder, or compact and redo lot of times, right? Here also we will have to change the powder, but what we do is you apply a normal stress. You can see that it's over consolidated powder, and this is an under consolidated powder, and it reaches a critical state, and at one point it starts moving, right? That's one, that's usually the pre-consolidation, pre-shear force. Okay. So after you pre-shear, you remove this effect under consolidation and over consolidation, you apply a normal stress sigma 1, which is little lesser than the pre-shear load. Okay. So when you apply those normal stress, then at one point it starts flowing or moving. So that's again the shear stress that needed to make the powder flow. So you keep on repeating that test by going to smaller normal stresses. Okay. So again, simple measurement, again as we talked about, it depends on the solid fraction too. So solid fraction will be changing for some of those shearing process. Okay. So that's why sample preparation is very important, and you'll have to be very careful when you prepare those samples for testing. Okay. So at those different shearing points, so again we get the relationship between the normal stress and the shear stress, right? So normal stress you apply, right? You are applying, and shear stress you get from the instrument, right? So you get this yield locus, and then you draw the minor and major Mohr circles, right? Then you get all other good stuff, all other values. And again, usually the final stress is called the endpoint stress, which we use for the major Mohr circle, okay, at which we draw the major Mohr circle. Again, you can prepare at different solid fractions, okay, and then repeat those testings. But again, the material flow function or the yield loci relationship will be different for those different solid fractions. Okay. Any questions? Simple testing, right? So again, simple testing, but it gives lots of useful information for when it comes to design. Okay, design hoppers and bins. So in general, again, we assume this as an ideal Mohr-Coulomb material. Okay, so that means the relationship between the normal stress and the shear stress is linear. Okay, again, that's the friction, right? So that's the internal friction coefficient. Okay, so again, my ideal Mohr-Coulomb law, the shear stress is related to the normal stress and with the intercept of cohesion, right? So that's one major assumption that we do, when we talk about this shear cell use and shear cell measurements, right? But the challenge is most of the, again, any food powder or most of the biological materials, they don't behave like an ideal Mohr-Coulomb material. Okay, the relationship is not linear. Okay, so why the relationship may not be linear for food powders or biological materials, or any material. In fact, you might see ideal Mohr-Coulomb material like glass beads, spherical, like those are uniform in size, shape, and surface characteristics. All others may not follow this ideal Mohr-Coulomb law. Okay. Why the regular powders does not follow Mohr-Coulomb law? It's not attraction, it's due to the presence of cohesion, inbuilt cohesion between those powders. Okay. So you take any biological material, it could be grains, powders, there will be some coefficient, inbuilt coefficient, okay. So you might not get a linear, I don't think I have those, yeah, the curve here for one example material. So usually you see a curvilinear relationship. At lower stress, it's non-linear, but when you increase the stress, the stress will overcome the inbuilt coefficient between the material, and then it becomes a linear relationship, okay. But at smaller stress, you see a curvilinear due to the effect of inbuilt coefficient between the particles, okay. So some example here again, coefficientless materials, very rare to find, but their coefficient will be 0, but for like example of stiff clay, this very high inbuilt coefficient, okay, that affects this behavior. Again, I've given some examples there. But, so we briefly, okay, this is the picture that I was trying to draw here, okay. So again, we talked about this, right? So we draw two circles, major Mohr circle and a minor Mohr circle. So using those values, you get all other, values: unconfined yield strength, major principal stress, minor principal stress, etc. Okay. So, yes, I indicated. So minor principal stress will be the stress from the walls when it directly relates to the stress from the walls. Okay. You can relate to ideal, any bin or hoppers too, right? So the walls will put some stress on the powder, right? So that will be sigma 2 or the minor principal stress. Any questions? Go ahead, think and ask me any question if you have. Is it easy to understand? Okay, go ahead.
Previous,
Yeah, go ahead.
sir, in two graphs, second graph is starting from near about 0, but in this graph it is starting from C. But in exactly C.
C is the coefficient, okay? Coefficient between the powder, okay? So that's not inbuilt, it's a measured coefficient, actual coefficient between the powder. For example, when you put bulk powder in the bin, okay? So there will be some coefficient between the powders, right, due to the effect of weight or other effect from the bin wall effect, okay? So that's what we're measuring using the C. That's the intercept, okay? So what I said was, for most of the materials, this relationship will not be linear, okay? Since most of the powders will have, or any material as we talked about here, will have some inbuilt coefficient, right? Due to their properties, chemical properties, etc., right? So that changes this relationship. So at lower normal stresses, the shear stress may not be higher than the inbuilt, stress from the coefficient, okay? So that might not change linearly with the change in normal stress.
When they are doing actually experiments, we get like that.
Yeah, it might be, that's a representative picture, okay, but it might not get exactly same, but you will see some curve.
But we are not getting linear process.
Yeah.
There will be some more chances there to.
Yeah, so if it's an ideal coefficientless material, you will get perfect linear. But you see from this graph, it will not be never be linear. It's very close to linear.
We are taking this point only near about that linear line.
Yeah. So closest to linear line. Okay. Yeah, go ahead.
Sir, if it is ideal coefficientless material, then why the intercept is the graph?
Oh, that's a good question. So this is not for ideal coefficientless material. So for ideal coefficientless material, it will be like this. Okay. Yeah, this is for any regular materials. Okay. It's a good point that you noted. Yeah. Any other questions? Okay. So again, we get the effective angle of friction from the major Mohr circle, right? So that's the angle that makes with the final shearing point, okay, or around that tangent to the major Mohr circle, okay, and then you get that angle as the effective angle of internal friction, okay. So we'll see where we apply this, okay. I'll show some examples too, okay. there's one important property that we measure from the shear cell analysis, okay? The angle that connects with the major Mohr circle, okay? I'm not going into those calculations, but it's a it's a lot of equations inside, and again it will take time too, but it's a simple way. But most of the instruments it gives directly, you don't have to do much math or analysis, anything. They throw, they spit out the numbers when you do the measurements. Okay. So the effective angle of internal friction in general is a weak function of consolidation stress. So at lower consolidation stresses it might change a bit, but at higher consolidation stresses usually they are plateaued, they don't change much. Okay. So this ratio also almost remains constant, okay, just for the angle of internal friction, but other properties will change. So same measurement, we talked about measuring one layer of powder moving over the other layer of powder, right? So for measuring the wall properties, okay, what we do is we use that wall material at the bottom, okay, and then put the powder and then measure the shear force that is needed to move this powder above this wall material. So one side it's wall and the other side is the powder, okay. So you can use and test the different types of wall material that you are interested in constructing a bin out of, okay. So if you are constructing an aluminum bin or a stainless steel bin, take a piece of that material and put it at the bottom of shear cell and then measure the wall friction. But most times the instrument manufacturers, they themselves provide those material samples for wall friction measurement. Okay. So very similar analysis. Your question? Go ahead.
Sir, we are here measure only friction between wall particles.
No, here it's between the material and the particle. Okay.
Like a lower plate or
So this is the wall material, and then the bulk solid will be above that wall material.
they are moving like that.
Yeah, we are moving. You see, the whole thing is moving. Okay. Any other questions? Okay. So again, for any shear cell measurements, ideally, you might need maximum 5 points. So 5 points of consolidation stresses, okay, and then measure the shear stress and then get the yield locus, okay. But again, I think Schulze developed this table, to that you can use as a reference point to get the pressures that you can use based on the bulk density of the material, okay. So based on the bulk density of materials, you can again use different pressures, and also based on the different sizes of silos, okay. So if you are using a large silo and the material bulk density is higher, very high, then he suggests to start with a 50 kilopascal measurements, okay. Again, that's the anticipated load that you will see, in the top of the bin, okay. Again, that's suggestion, but ideally you will have to calculate the loads within the bins and then use those loads to choose the appropriate normal stresses for testing. Okay. So how do we, any other questions before moving on to the next part? No?
Sir, those walls you for the test in the table, so these are attached with the surface. I think these are not attached. So when they will move, some powder which have small particle size, they can get out from the.
Usually not, those are very sealed. You don't see that powder going into those under the, sheets very much.
To give more load on that.
What's that?
For that we have to give also more load on that.
For the powder to move?
Powder to move also. So powder to be inside those walls. We have to give more load on the walls.
Not clear. So you are saying to confine within these walls? So yeah, you'll have to attach it. It's not loose sheet metal, okay. So you'll have to attach it. And again, instruments, they have good attachment, so that's fixed and they don't move. the sheet metal. So when you apply normal stress and start applying shear force or shearing stress, only the powder moves. Okay, so it doesn't usually doesn't move. Go ahead.
Previous slide,
Yeah.
like it is mentioned, 50 kilopascal is the maximum lateral pressure it can withstand on the top or on the bottom.
So it's usually again, that's a good question again. Usually you can if you read the Schulze's book, you can start with 50 kilopascal, assuming at the bottom. Okay, but you can get anywhere, right? So he doesn't give any clear indication of whether it's a medium, large, what size, etc. So that's why I said if you have a bin, you will have to calculate based on the dimensions of the bin and then use it. This you can take it as a starting point, but this is not fixed on stone or anything. Okay, does that clarify? Okay, so you will have to do your calculation, but it's kind of rough indication. Okay, any other questions?
So mainly it is used for finding thickness of the bin.
No. So how it flows, getting the hopper angle, we'll talk about that examples in a minute. Okay, how do we use those properties? Okay. Okay, any other questions? Okay. So how do we, again, talked about this, right? Why grind silos or any powder solid materials bins are tall, narrow, but liquid tanks are shorter and wider, right? So some of you gave the answer correct, so I'm not going back. But again, this is a Jansen's equation that we commonly use to get the stress and both vertical and the radial stresses in bins. Okay, I'm not again going into the equation yet, but in general, again, the only difference here is K is the pressure ratio. Okay, so it's calculated from the angle of internal friction, right? Anyone remember the formula? Okay, sine phi, it's not sine theta. Okay, just quickly, it's a small correction. That's 1 minus sine angle of internal friction over, that's where we use angle of internal friction, okay, to calculate the pressure ratio. Okay, so you calculate either one of them, and then using the pressure ratio, that's K, you calculate the other stresses, either vertical or radial stresses. Okay, and then again, mu is the coefficient of friction, Z is the height from the top surface. What is that? Some joke? No? No, go ahead, you can smile, but if it's a joke, you'll have to share, okay? So again, D is the diameter of the bin, and then gravitational force. So you can calculate the vertical, ZZ is the vertical stress and RR is the radial stress that acts to the side, okay? So what happens, in a solid, this amount of stresses or forces from the friction above almost, at about this, when this value becomes 3, so their value, the stress values are asymptotic. Okay, that means they doesn't change. Okay, so approximately, if you have a tall bin above like a meter or 2, again depending on the powder properties, there will not be any vertical stresses. The effect of vertical stresses will be low, okay, on the bin. But again, but if you are increasing the diameter, then the stresses will go up. So that's why we limit the diameter, but just to keep the vertical stresses low and the effect on the bin and hopper low. Okay, but for is incompressible liquid, any most of the fluids. So again, we know the equation, right? So rho g height. So with increase in height, the stress also increases, right? Goes up. So again, these stresses independent of depth, and then the surface stresses. So most important parameter here is, at least for particulate material, is the diameter of the bin. Okay, so keep it shorter so that you can get away with a minimum thickness bin wall or strength of bin wall. Okay. hopper stress field. So again, I'm not going into those stress tensors, but I believe it's available online. If you Google and see Jeniker's analysis of hopper stresses, you should be able to get those stress acting on powders in a bin. Okay. Again, the stresses in the mass flow hopper. Again, he ideally used mass flow hopper. Since above mass flow hopper, you can see, if you are constructing a funnel flow hopper, it's beyond the region of mass flow, right? Then the powder flow will not be uniform, right? So ideally use the mass flow hopper. So dependent on the angle of internal friction, wall friction angle that we measure using those wall material, and then the hopper wall and the vertical, that's the angle of hopper, okay, or hopper half angle or hopper angle, okay. So how do we get those? I'll give you some example here. So if the angle of internal friction is 50 degrees and the angle of wall friction is 20 degrees. So the good thing is, you don't have to do most of these calculations. So Jeniker has done all these calculations and he has developed those charts. So we just have to use those charts and find the appropriate angle, okay, for different types and shapes of hoppers. Like if it's a conical hopper, if it's a rectangular hopper, I'm not sure if I have, symmetrical slot outlet hoppers, it's kind of slot at the bottom that opens. So for those different types of hoppers, he has done all the calculations. So you just the wall friction angle, flow factor, and then you can get the angle of hopper. Okay. So wall friction, again get the appropriate wall friction angle, relate to the angle of internal friction here, and get the hopper half angle. Okay. So it's very easy to use. I think I have an example somewhere. Any questions on this? Easy to use, right? So just get the data from shear cells, directly apply on these charts and get those values. Okay. Any questions? Again, same for different shapes of hoppers also. He has developed those charts, which again. Oh yeah, this example again, if the effective angle of internal friction is 40 degrees and the angle of wall friction is 18 degrees, determine the maximum wall angle at which a mass flow can occur. Okay. So again, we know that 40 degrees and 18 degrees, right? So you pick the 40-degree curve, okay. Oh no, that should be 18-degree curve, and then hit the 40 and you get the appropriate angle. Okay. So simple and easy way, okay, to find the appropriate hopper angle. Any question? Go ahead, yeah. No question. Prakash, any question? No? Okay, so simple to use, okay. So to avoid, again, we talked about this, right? So avoiding flow stoppages. So if you're not able to use that mass flow hopper, okay, what happens is, again, we talked about this. So the stresses at in this region at least should be higher than the stresses at this in the unconfined yield stress, right? So that this will push the material down, and then it's breaking the surface and flowing. The powders are flowing. Okay. So in general, that's what we try to find out. So at different levels of the bin, what will be the stresses acting on the powder, and what will be the appropriate angle at which there is no unconfined strength building on the powders. Okay. So that if you change this, the unconfined yield strength will change and the powder will be flowing freely. Okay. Is that clear? Any questions? No? Okay. So again, for a mass flow hopper, again, it's, we went through those examples, right? We can get the hopper flow factor too. So for different angles, we can get those relationships. But as I said, most of the relationships, he has already plotted them. So it's a function of, again, we saw this, right? It's an angle of internal friction, angle of wall friction, and then the hopper angle, right? So it's very similar to material flow factor or material flow function. So we can derive the Hopper flow factor, that's from the consolidation stress and then the stress developed in the material. Okay. So the stress developed in the material is the stress here in that powder region. Okay. And then sigma 1, and that's a consolidation stress, and then how much it flows, how much it takes to make the material flow. Okay. So Hopper flow function we can again draw for different angle of internal frictions between the powders, in that we can use for getting the, I'm not sure if I'll skip these. Yeah, we can use these information to get the discharge rates too, or Hopper, again Hopper half angles too. Okay. I'll skip the example. Same example, if you know the wall friction angle, if you know the again angle of internal friction, you can get the appropriate angle for mass flow. Okay. So if you check this book, Principles of Powder Technology, you will see more examples on this. Okay. So again, yeah. So as we talked about, so he developed for mass flow hoppers. Okay. So he developed those relationships for some areas where mass flow occurs. So beyond that region, so then you can assume the flow will be either funnel flow or it doesn't flow. Right. So at those conditions, again you will have to use those external flow aids like external vibration systems, pneumatic systems, etc. Okay. So if you couldn't design that Hopper angle, then you may not get mass flow, then you will have to use some external flow aids. Okay. So again he has done these minimum outlet diameter calculations for different RFI sizes in on all those Hopper half angle calculations. Okay. I'll not go through those. Okay. So flow rates, you would have heard about Beverly equation and Johansson equation, right? Maybe some of you at least. Okay. So again, I believe it should be in Saha and Singh, by that you use for ARS, right? So for coarse particles, it's very commonly used for coarse particles to get the flow rates. Okay. So fine particles, it's difficult to use these or any type of relationship, because there will be high effect from air, right? If it's very small particle, it can fluidize and suspend in air, right? And there will be high cohesion between the particles too. Then using those relationship will be difficult. Okay. Almost I'm not going through those equations. Only difference is for Beverly relationship, the units must be in SI units. Okay. Then only that equation we developed using SI units. So you'll have to use again kilogram, meters, etc. So from the outlet size, again constants and diameter of the particle, you can get the discharge rates. Okay. Same for Johansson relationship. It's mostly used for circular orifice openings, circular outlets. But again, you can use any type of unit system, but only thing, the units should be consistent. If you are using metric system or SI system, use the same units for both for all the constants in the equation. Okay. So again, both equations, again you can say the discharge rates highly depend on the bin opening size by the power of 2.5. So if you increase the size of the bin outlet, then the flow rate or discharge rates will be high, right? So that's why we talked about flooding of materials yesterday, right? So if the outlet size is too high, then the discharge rate will be too high, and then it leads to flooding of powders. Okay. Any questions? No questions? We're almost done with the shear cell. No questions? Okay. So we'll talk about again improving flow performance. In particle size affects the cohesive forces, right? Interactive forces, van der Waals forces, static charges build up, etc., etc. So in general, larger particles have a greater inertia and less cohesion, right? For example, if you are working on agglomeration and compaction of powders, okay, you wanted to make them flow through small funnels and small tubes. The small powders, it'll be very difficult to make them flow through those small systems, conveying system. What you have to do is agglomerate them to a larger size, and then you can make them into other useful products. Okay. Particle size distribution, so more uniform size distribution, so it will have better flow behavior. So if it's highly mixed particles, then those smaller particles will fit into the white space between large particles, and then it increases the surface forces, right? Surface interactive forces. So shape also, ideally more spherical particles will have better flow, right? But if it's irregular, then there will be more interlocking between the particles, right? So it's more text. So surface roughness too, there will be higher I'll quickly go through. So if the surfaces are smooth, then there will be stronger van der Waals interaction. Okay, but if the rough surface, then there will be more electrostatic forces or static charge built between those particles. Okay, so either way, if the particles are small, you will have to deal with one or the other forces. It could be either van der Waals or it could be electrostatic forces. So interstitial air, lower permeability or high low porosity will affect the powder flow. Right, I gave you one example yesterday, right? Wheat flour unloading, you always see industry use some additional pipes of air flow through that trucks and containers so that the material flow because of low permeability. But again, larger permeability or larger white space will be better for flow. Okay? So if you can avoid the size distribution, if you can make them more uniform, then the particles will be more uniform or tighter distribution, then the flow will be easier. Moisture, again, you all know, high moisture, low moisture effect. So when you wanted to measure the flow properties, so it's always better to use some shear cell measurements rather than using Kars indices or Hassner ratio or angle of repose, etc. Okay. So as you have seen, if you use shear cells, it gives actual values that you can use for design, hoppers, bins, and also understand powder flow properties. Again, if it, if the powder does not fit in mass flow category, then usually we come with different ways of improving the flow. Coating the wall with some frictionless coatings, or air venting, active feeding, etc. Active feeding is in general at the bottom of the bin. They will have a auger type of system, conveyor auger that pulls the material from the from the bin. But there are tons of these flow aids or flow instruments that helps with flow from the bulk powder bin. If you Google, you'll at least find more than 100 types of devices, etc. And again, empirical benefits, it helps us rank the materials but doesn't give any much theoretical understanding on that. So I didn't talk about rotational shear cells, but there are annular and Pascal shear cells. So translation is, as I've shown the picture, it moves like this horizontally, translation. Rotational shear cells, it rotates, the top part rotates, so that's the way it works, almost same measurements. And there are tons of standards for powder flow measurements, ASTM, USP, etc., that you can use to calculate these. Lots of books and publications on powder flow. Some of these are Jenike's papers are, if you are interested in powder flow, Jenike's papers are very good. And then Johnson is okay. Yeah, Schulze's book, Schulze and Netterman books are very good, if you understand more about powder flow. Okay. Martin Rhodes' book gives the overall introduction about particle technology, but not much in-depth information. But Netterman and Schulze gives better, math and physics behind powder flow. Okay, that's it for this lecture. Any questions? You can stop, take a break.